just a quick summary. Here are the different forms that I told you I was going to look at, as well as what y should be based on our previous examples. If f is equal to kt to the m, then we want to set y up as a polynomial of degree m. If f is k e to the rt, then y is a e to the rt. And if f is either k cosine bt or k sine bt, then y of t is a cosine bt plus big B sine little bt. And if f is a product of any of these, then we would just take the products of y. So let's do an example for that. Here I have y double prime plus 4y equal to 5t squared e to the t. Since I have a product here, I'm going to let y be equal to a product. The fact that this here is a t squared tells me I want y to be of the form a2t squared plus a1t plus a0. And the fact that this is an e to the t tells me I also want something of the form a constant times e to the t. And I used a d here for a reason that I'll hopefully make clear in just a second. I could go ahead and distribute just the d here so that I have a2d squared, a2dt squared plus a1d times t plus a0d times e to the t. And then these both are just constants, and a constant times a constant is just another constant that I'm going to call a. Same thing with a1 times d, that's just a constant that I'm going to call b. And a0d is a constant that I'm going to call c times e to the t. So while we should consider all the possible combinations whenever we multiply out our y's, it is very possible that we can simplify it to have fewer terms and fewer coefficients here, fewer unknowns. Now that we have this, we can find y prime. We will have to use the product rule. The derivative of the first would give me 2at plus b times the second plus the first, which is at squared plus bt plus c, times the derivative of the second. Y double prime, once again another product rule. The derivative of the first would be 2a times the second plus the first, which is 2at plus b, times the derivative of the second. The next piece, I need the derivative of the first, which is 2at plus b, times the second plus the first, which is at squared plus bt plus c, times the derivative of the second. And now we want to plug this back into our original differential equation. So it says y double prime. That's 2a e to the t plus, we'll notice that these two terms are identical, so I'm going to go ahead and add them and make this 4at plus 2b e plus at squared plus bt plus c e to the t. And then we need to add 4y, and I'm going to go ahead and distribute the 4 to make this 4a t squared plus 4bt plus c times e to the t. And this should be equal to 5t squared e to the t. And once again, we could divide everything through by e to the t and get rid of all of these. And now we're going to look at coefficients. I'm going to start with coefficients of t squared. There's a t squared term here, here, and here. That tells me that the coefficients of t squared are a plus 4a, and that needs to be equal to 5. We scroll down a little bit. That tells me 5a is equal to 5, or a is equal to 1. Looking at coefficients of t, I have a 4a, a b, a 4b, and on the right-hand side I have 0. This tells me that 4a plus b plus 4b is equal to 0. We already know that a is equal to 1, so I have 4 plus 5b is equal to 0. We can subtract 4 and divide by 5 to get that b is equal to minus 4/5. Looking at our constants, we have a 2a, 2b, c, and none on the right-hand side. So that gives me 2a plus 2b plus c equal to 0. We already know a is 1. We already know that a is 1, so that would be a 2. Minus 8/5, since b is minus 4/5, plus 2c equal to 0. That tells me that 2c is equal to minus 2/5, which gives me that c is minus 1/5. So I have a times t squared plus b times t plus c, all times e to the t for my solution.